I will introduce the generating functions in this video. To talk about generating functions, I'd like to start with a reminder and an overview. So let x be a random variable. RV stands for random variable as usual. And if x happens to be discrete, meaning that it can take on countably many values, which I'm going to call x1, x2, x3, and so on, then the expectation of a function of x, assuming that this expectation exists, is going to be the function values times the mass function at those particular possibilities xi's. If x happens to be absolutely continuous, so okay, let's write it out. If x is absolutely continuous, then the expectation of a function of x, assuming that this exists, is written as the integral of the function value gx times the density of x. So this is the probability density of x, probability density function. Okay, so just a generic reminder. So what's coming next is I'm going to write expectations of various functions of x, and I just want to give you a small overview of kind of a zoo of useful characteristics of distributions, if you wish. So just an overview. Everybody heard about the moment generating function in probability 1. The moment generating function was denoted by mt in probability 1 and is defined as the expectation of exponential of tx, both for continuous or discrete. And this always exists, however, it could be infinite. If we don't have all second moments, then it could be infinite. So that's a problem with the moment generating function, but it's quite nice and easy to work with. The generating function is defined to be, the notation is p of s, and its expectation of s to the x power. The usual way of using it, so the usual scenario is for non-negative integers and s between, well, often 0 and 1. Sometimes people go to negative, but it's enough to look at between 0 and 1. Okay. The other one that some people use in some circumstances is called the Laplace transform. The Laplace transform is often denoted by f hat of lambda, and it's very similar to the moment generating function except for a negative sign up in the exponent. People usually use this for non-negative real random variables and lambda positive. Okay? That's the usual way of using it. The point is that if lambda is positive and x is positive and it's not negative, then this is almost between 0 and 1, so this will always exist and have nice properties. And then when one wants to go general and prove very nice strong generic theorems, then one can use something called the characteristic function. And in fact we are going to use the characteristic function later on. And that's usually denoted by phi of t. So here we actually go out to complex by making a complex twist to the moment generating function by adding the complex unit I up in the exponent. It turns out that this always exists. It's always nice. And it's mostly complex. So we need to go out to complex in order to work with the characteristic function, which is fun, but and it's very powerful and very strong, but it can be a little bit more complicated than using some of the other things. What I'm going to do here for the next couple of videos, and what we're going to do in class for the next couple of weeks, is we're going to concentrate on the generating function for non-negative integers. Okay, so this is what we're going to do now, and later in the unit we're going to take a close look at the characteristic function as well. Okay, so let me then define the generating function. So from now on, at least in this part of the unit, x is going to be a non-negative integer random variable. There's going to be one small complication, namely x equals to infinity might also have a positive chance. This will be useful later on. Okay, so it's like a positive integer, but we also add in some cases the value plus infinity for the possible range of x. Okay, and the generating function is therefore defined. The generating function for the distribution of x is defined to be, so first of all the notation is capital P of S, and is defined to be the infinite sum of S to the I and P of I. And we do this whenever S, well, okay, we do this definition for all S, but this will make sense usually when S is between 0 and 1. Let's see what we can say about this generating function. So first of all, P of 1 is the sum from 0 to infinity of 1 to the I, Pi, and we are used to saying that this is 1. However, in this case, I'm going to say it's less than or equal to 1, because this thing is actually, so why did we say it's 1? Oh, now you see it, sorry. Okay, so again, so P of 1 is going to be the sum of the mass function values, right? Because S equals to 1 gives you the sum of the PI's, and I say it's less than or equal to 1. Why do I say it's less than or equal to 1? We used to say it's 1, because what is this really? Well, because these events are disjoint. These events that x is I, when x is my random variable, are disjoint. Therefore, the sum is equal to the probability of the union. What is that union? Well, that union is that x is either 0 or 1 or 2 or and so on, or any integer. This is exactly the probability that x is finite. Okay? If x is a proper random variable, so x is proper when this is 1. Probability x is finite is 1, okay, being the sum of the mass functions, and x is improper or not proper when it's smaller than 1. So if you look at 1 minus the generating function at 1, notation might be a bit confusing. This is my capital P, this is my small p, okay? So this thing is 1 minus the sum of the probabilities for all integers, and that's exactly the probability that x is actually equal to infinity. Okay? Now, when x is proper, then of course the sum of s to the I times pi is exactly the exponential of s to the x. And in fact, when s is less than 1, then even when it's improper, it's the same thing. Okay, another thing I want to notice here is that if you go to positive 1, you still are definitely able to sum this up. If you go to s equals negative 1, then even then it's absolutely summable. If you put an absolute value around s, then it's summable. You just get the sum of the pi's is less than 1. So the radius of convergence of this series, radius of convergence around 0 is at least 1. When you go plus or minus 1 from 0, so when s ranges from negative 1 to positive 1, this thing will always be absolutely summable. So there is no problem with convergence on the interval minus 1, 1 for s. Okay, so the radius of convergence is at least 1. Okay, so these are the first and most important properties of a generating function. And then let me proceed with some more good properties of this. So the next thing I want to do is observe what's happening when I differentiate a generating function. Suppose I want to differentiate a generating function n times. What do I get? So I want to differentiate n times the sum from 0 to infinity of s to the I mass function at I. Okay, now anybody can check that at least when we have absolute convergence here, so when s is between, say, s mod is less than 1, then if s is strictly less than 1 at least, let's do strictly less than 1, then one can swap the derivative with the infinite summation. This is not always straightforward, but in this case one can do that and find something interesting. So the n-fold derivative of s to the I is what? Well, the first derivative is going to be I times s to the I minus 1. The second derivative is then another factor I minus 1, and now I have s to the I minus 2. And the nth derivative is going to be I minus n plus 1, and the power I have left with is I minus n. Okay, so let's just check that it works. For n equals to 1, I have I, and actually I have to stop at I because this term is I, times s to the I minus 1, so that works. For n equals to 2, I have I times I minus 1, s to the I minus 2, so it works, and so on and so on. Okay, so that's what I have. Another thing to notice is that actually for the nth derivative, I don't need to start this sum at 0. In fact, I could have started this sum beforehand, but even in this form, I could say that maybe it's better to say it here. So when I do the nth derivative, then in fact the nth derivative of s to the I is 0 whenever I is less than n. So instead of saying it's going from 0, I'm going to make a correction here. I'm going to say that it goes from n to infinity. This product is 0 anyway before n, or you could just say that s to the I differentiates to 0 if I do n-fold derivatives whenever I is smaller than n. So I'm going to look at this sum from n. Okay, so now the next thing I want to do is take the same n-fold derivative but plug in s equals to 0. And let's see what happens for s equals to 0. Now, if I minus n, so my first term is the nth term, I equals to n. At I equals to n, what I see is n times m minus 1 times ... 1. So that gives me an n factorial. Then at I equals to n, I have a s to the 0 power, and s to the 0 is 0 for all s's. When I plug in s equals to 0, that, if you want by convention, it's 1. And then p at I equals to n, so that's my first term in that summation. Then when I is higher than that, I have some factor here, but when I is higher than n, then I have a positive power of s, and then this whole term for a positive power of s at s equals to 0 just gives me no contribution whatsoever. So I end up with n factorial times the mass function of n, of x at n. Or if you want, n factorial times the probability that x equals to n. And that's very nice, because if I have a generating function and I want to find out about the mass function, all I need to do is differentiate n times, divide by n factorial, and I get my mass function value at n. In other words, ps around 0 uniquely determines my distribution. I am assuming here, of course, that we're talking about non-negative integer axes. Okay, so the generating function is one-to-one to distributions, to non-negative integer distributions. The other thing I want to emphasize here is that if I now take the nth derivative at s equals to 1, then what I have is, let's take another look here, the nth derivative at x equals to 1. S equals to 1 just gives me no contribution here, so I end up with the sum from n to infinity of I minus 1 dot 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 I minus n plus 1 and then pi. Okay, and now I need to be a little bit careful. So what this comes down to is, first of all, nothing is negative because I goes from n up, so nothing is negative here, and this sum will always make sense. It might be infinite. Now if x is proper, in other words, if x is always finite, with probability 1 is finite, in other words, we're looking at all possible contributions of the probabilities from n up, then what I have here is exactly the expectation of my random variable x times x minus 1 times x minus n plus 1. Okay? Why is that? Because in order to calculate this, I have to do exactly this sum from 0 to infinity, but any I value below n is 0 anyway, so it's the same term. And this is called the nth factorial moment. So this whole thing is the nth factorial moment. Okay? In particular, if I do the first derivative, and x is proper, so with probability 1 it's finite, then I can straight away get the expectation by differentiating p and plugging in s equals to 1. When n equals to 1, then I just have one term here. This is n terms, right? So when n equals to 1, I just have one term here, the expectation of x. So to find out the expectation of my random variable, once I figure that it's not infinite with any positive probability, all I need to do is differentiate the generating function and plug in s equals to 1, which is quite similar to the moment generating function, which probably many of you are used to. What if I want to do the variance? Well, again, if x is proper, so I still need to assume that, then if I do expectation of x minus 1 here, that's just coming straight from the second derivative. Now, this is not exactly my variance, because what is this? This is the expectation of x squared minus the expectation of x, which is not my variance, but almost. It's the variance, which would be expectation of x squared minus e of x, but in the variance, so the variance would be expectation of x squared minus square of ex, and I don't have that, so I'm going to add back the square of ex, but I have instead minus e of x. So this second derivative of the generating function at s equals to 1 is actually variance plus square of the first moment minus the first moment. So if I figure out the first moment, I figure out my second derivative, then I can figure out my variance as well, going back this way. So the generating function also generates moments in a slightly different way than what we used to with the moment generating function. We have these factorial moments instead of proper moments, but those are just some algebraic transform of the actual moments of my random variable. I want to finish this video with a theorem, which I'm not going to prove, and that's about going backwards. Suppose somebody gives you a function and asks you, is that a generating function? And the theorem answers this in the following way. So a function that goes from 0, 1 to r and is continuous function. Notice that the generating function, as we defined it, actually has this property. So generating function, if we define it from 0 to 1, it's going to R and it's going to be continuous. So this continuous function is of the form, I'm going to call this continuous function PS, okay, is of the form PS equals to the sum from 1 through 0 to infinity s to the I pi for some numbers pi at least 0, if and only if for every n non-negative integer and for every real number s strictly between 0 and 1, the nth derivative, so that's a short for the derivative, the nth derivative of n, or of p. So that's a short notation for the nth derivative of ps, okay? This thing exists and is positive, non-negative at least, exists and is non-negative. I'm not going to prove this. It's kind of plausible because this is just a power series, and if we just do so each of these terms is actually a convex function and some positive coefficient here. So it's quite plausible that that there is a Taylor series in this form if the derivatives are all non-negative and the coefficients of the Taylor series is non-negative. I'm not going to prove this theorem, but this is what makes a generating function. Now, this is usually not the way to find out whether a function is a generating function. Much more often what we're going to do is we are actually going to find the Taylor expansion, or in some trick we're going to find these coefficients pi's, maybe not by differentiating, and then we can just read off the mass function and can decide if it's non-negative and if it's a mass function. But it's still good to keep this theorem in mind, that a continuous function that's given to you is going to be in this Taylor series with positive coefficients, or at least non-negative coefficients, if and only if all the derivatives between 0 and 1 exist and is non-negative.